what I'm going to do first. Hitting record. All right, so I'm going to go through the notes. There's not a whole lot of notes. I'm going to kind of freestyle it on the board this time. I did post the equations, which I think is a helpful touch. And then once we're done with the notes, we're going to move on to the problems. But before we do that, I will open the floor for any circular motion questions or confusions, or really any questions about any of the review material or the tests that we've been going over. So is everyone understanding and in a good place? Good. Awesome. Okay, so without further ado, this is one of those units I feel like was a little bit confusing, but is based on just a couple of fundamental ideas. And so we want to hammer those home. The one thing I will have to say is that the AP exam is not generous with what it includes on the reference table for this unit. So they give us centripetal acceleration, which is really nice. It's an important one. I don't want to remember that, so it's good that they have it on the reference table. They give us period is equal to 1 over frequency, which will come up, so that's good. They also have some rotational motion stuff. It's very often when you have something rotating in a circle, they might ask you, what is the angular velocity or something like that? How many degrees does it travel in a given amount of time? So if you're given period and frequency, you can find it with this information. Rather useful equation that they give you on the reference table. They also give you what big G is for gravity, so you don't have to remember that number, unlike me, who is cursed to remember it for all of time, along with the speed of light and a lot of weird numbers I don't think need to be in my head. Also, we have, hold on, are you guys muted? They might be muted. Yeah, you were muted, so we couldn't hear anything, but if you were saying something, you can talk now. All right. So in terms of what you have to memorize, the big one is the gravity equation. Yeah, not found on the reference table. I looked. It is very, very sad. Oh, no, wait. I found it. It's just not where I thought it would be. Yeah, so this is good. So scratch that. Not on there. I was very confused why it wasn't on there. So turns out it is on there, which is nice. One thing they don't give you is what if instead of G is equal to 9.8, like what if you went to a place where it was a different number, like the moon or Jupiter or something? There's an equation we talked about that you can derive using this to find G at any given location. So if they ask you about a foreign planet and they don't give you the acceleration to gravity, you can calculate it knowing big G and the mass of the planet that you're going on. And lastly, I wanted to put on there the equation for speed or average speed around a circle. I made a big deal out of how average speed is just distance over time. The distance around the circle is 2 pi r. And the time it takes to go around the circle is the period. And so you get this equation, V is equal to 2 pi r over period. And that equation comes up way too much. It comes up very often. And so that one, if there's one equation you memorize that's actually required to be memorized, please memorize that one. All right. So any questions before we move on? Okay, very good. So first thing I want to talk about is centripetal force. So imagine we have an object and it's going around in a circle. Which way does the centripetal force point? Yeah, it always has to go to the center. So there's a lot of confusion around centripetal force. Normally, I think you guys did a great job this year of not falling into many of the traps. But number one, not a force by itself. Okay, centripetal force is a label that we give to forces. Last week, we talked about all the different kinds of forces you could have on an object. We talked about gravity, talked about tension, we talked about friction, we talked about normal force. Centripetal force could be any of those, but it can't be its own force. So for instance, if they say, hey, draw a free body diagram for this object, you can never put centripetal force on that free body diagram. That's not something you can do. The reason is because centripetal force is caused by probably something else, something like a tension force pulling it toward the center if you're spinning it on a string. Or it could be a normal force if it's like banked around like some kind of a ramp, like a bowl or something. But yeah, it could be any other force. And the key idea here is that you never put free body diagrams, you never put centripetal force on a free body diagram. It is just a label, okay? And you calculate it by this. Centripetal force is equal to net force that is going into or out of the circle. Okay, so that's the main idea, that you don't add up all of the forces on an object. Centripetal force does not always equal the net force on an object. An example here, if in my picture here, this way is up, okay? What would be a force acting on this ball? There's tension. Sure, tension or whatever the centripetal force is. And what's the other one? Gravity, right? So we would have two arrows. We would add these up and we would get some kind of net force that doesn't point toward the center, it points this way. Okay? So if you add in all the other forces, it can get kind of complicated. When you're talking about what is the centripetal force, it's only talking about forces that are going toward the center of the circle or away from the center of the circle. So positive, you add them up if they're going toward the center of the circle, and negative if they're going away. Simple enough? Okay. So centripetal force, centripetal acceleration, and tangential speed. So let's look at that object more closely. Let's say we've got a ball in a circular path, and there is clear as day a string connecting them like this. We'll say it has a tension force pulling downward on it, okay? If I wanted to label the centripetal force, we did that a moment ago. In this case, it literally would be tension. Which way would the centripetal acceleration be, and which way would the velocity be pointing? Mm-hmm.
Velocity, it's going like clockwise.
Sure. So we'll say it's rotating this way. It's counterclockwise.
Then it's going straight to the left.
Straight to the left. Yeah. So centripetal acceleration points in the same direction as centripetal force. So let me clear this out. Toward center. And also toward center. Okay, good. And then what kind of, you say that the velocity is going to go this way, right? Yeah. Okay. So just to be clear, it's a very weird diagram to have a velocity and an acceleration arrow in the same thing. Normally your arrows are only supposed to represent one thing, like force or speed, like they're not supposed to mix. But a circle problem is often a case where you're asked to do one or the other or both. What kind of an angle does this make? Yeah, it's a 90-degree angle between the between the speed and the acceleration. So perpendicular to acceleration. Now, this basic diagram here, something I probably made you draw way too many times, is important because not only is it going to apply to circles, it's going to apply to any kind of curved motion. So if they say an object is doing this, okay, and they asked you, what's the centripetal acceleration when it's at this point? Which way is the centripetal acceleration going to be moving? Yeah, in this case, it would be up. If they had some kind of a pendulum system where it was swinging back and forth between 2 points, and they asked you, which way is the centripetal acceleration pointing at that location? Which way would it be going? Toward the point of rotation. Okay? And velocity will always be tangent to the surface or perpendicular to the radius. So in this case, so basically, I've seen questions on the AP exam. I don't know if there would be one at that point because it's not curved. I've seen questions on the AP exam where they don't give you like a perfect circle. And then they expect you to be able to draw these things. And so I just wanted you to realize that this pattern continues throughout all curved directions. Okay. Also, what is the equation for centripetal force that connects it to centripetal acceleration? Noah, do you remember? No. Okay, so what if it was not centripetal force? What if it was regular force? How do you connect to regular acceleration? Force equals mass times acceleration. So centripetal force is equal to mass times centripetal acceleration, correct? Crazy, right? This is a really easy equation to remember, but it's important because then you have that other equation for centripetal acceleration. How did that one go? Complicated one. It's on the reference table. Stare at it harder. Yeah, v squared over r. We went over that in the last slide or the slide before that. So oftentimes you can get an equation for centripetal force that looks like this. mv squared over r, like that. Yep, and so that's how you connect all three of these variables, okay? You've got FC, you've got AC, and you've got velocity there. Okay, as long as you understand that relationship, that's 90-ish% of circle problems. Any questions thus far? Hopefully it's all coming back. I got a message in the chat, just making sure it's not a question. All right, Tom, you just take off when you need to. All right. No, he's gonna stay for a little bit. All right, so acceleration due to gravity. I wanted to talk about the equation I pointed out at the beginning. Little g is normally equal to 9.8 unless it is anywhere else in the universe except the surface of Earth. This includes if you're on Earth, but then you go up a significant distance. If you reach a higher altitude, you're going to have a different g. As soon as you leave Earth's surface, you're going to have a different g. So therefore, you need an equation to represent it. And so I'm going to give you what is the equivalent of a mathematical proof for this equation. Ready? No, this is going to be nuts, all right? It's going to be nuts. Your head's going to hurt. It's going to be super hard. You'll never remember it, okay? So FG is equal to FG. Did I lose you yet?
No.
No, okay, yeah. So one equation is equal to the other. Makes sense, okay. What if I said calculate FG of a block and it had 3 kilograms on it? How would you calculate it? What would be the equation you use? Mass times gravity, right? So we can replace one of these with mass times gravity because the weight or the FG of an object is equal to mass times little g, right? Regardless of where you are in the universe, whatever the g might change depending on where you are in the universe, but the equation won't. Okay, you can always find the force of gravity with this equation. Zach, if I wanted to make this problem super hard and I gave you the mass of the planet and the distance away from it, how could you find FG in that case?
That is G, big G times M1.
Or I'm gonna change it up. So it's M1, M2, but I'm gonna make it big M for the mass of the planet and little m for the mass of the thing. All right.
Over R squared.
Over R squared, right? All right. Now, Noah, what is the letter that these two equations have in common? Little m. So we can divide both sides by little m. Now I get this equation. G is equal to big G times big M over R squared. So that's how you find the acceleration due to gravity anywhere in the universe. You take, so they say Jupiter, you plug in the mass of Jupiter, you plug in how far away you are from the center of Jupiter, and then you multiply that by big G, and you will get the acceleration on Jupiter. Another thing to point out is that when we're talking about these things, the R is the distance away from the centers. So you want to start at the center of each planet or each object and go from there. Sometimes they'll say something like this is a baseball or a satellite or some small object that the center really doesn't matter. But the center of like the planet could really matter because it might require you to add a radius before actually calculating how far away the ball is or whatever it is from the planet itself. Good. All right, I think there's one more slide. No questions on Zoom by the look of it. All right. So the last slide I wanted to talk about the big equation, which I'm so happy I was wrong and it actually is on the reference table because that's a lot of letters. Okay. So the main thing with this is the number one thing they're going to ask you is if this changes, what happens to the force? That is the number one thing they love to ask about this problem. All right. So if I doubled big M, tripled little m, and then, I don't know, quintupled times 5, quintupled. Okay, so that's times 2, times 3, and times 5. Okay, if I made all those changes, what would happen to my force? What number would I have to multiply it by in order to actually get this to be the correct answer now? So normally they don't give you a lot of numbers. They don't ask you to plug in the different masses, but they do want you to show how all of these would change. So G, big M would be double M, and then tripled little m, so 3 little m, over, in parentheses, 5r squared. So basically, whenever they give you a change like this, and now we're going to double the radius, or now we're going to triple the smaller mass. What you do is you just plug in the numbers with the letters, and then you pull out all the numbers. So 2 times 3 gives me 6 on the top here, and then 5 squared on the bottom. And that should be equal to all the same stuff we started with, GMM over R squared. And so basically, what would change? Well, we would have an initial force of just FG. That's what we would start with. And then at the end, we would have a force that is 6 over 25 FG. That's what would happen if we made all those changes. The force would change by that much. And so it's very often to get questions where they ask you, how much does it change and what that looks like. So any questions on my quick rundown of the entire unit? Okay, so this is the opportunity for anyone to ask any questions about circular motion, the AP test, or anything we've been doing in class. Speak now. Or something. Something. Okay, so at this point, I would like everyone to open up the review problems that are on the Schoology page for this review session. So if you haven't been here before, you go to Schoology, you go to AP test review, I think the folder's called, maybe. Preparing for the AP exam, that's definitely what it's called. And then in there, you'll see review sessions and you'll see session 3. And then you look for review problems. So starting here, AP review sessions, session 3, review problems. No matter how far we make it today with these problems, I posted the solutions to both of them so you can check them out. So I want you to open up the problems and I want everyone to take 10 minutes to look at the first problem and get as far as you can into it. So I'm putting 10 minutes on the clock. Try your best to answer this problem. There's 1, 2, 3 questions, and the first one's got 3 parts. There's a bucket rotating around in a vertical circle, and the bucket is full of water. The things I do. Backwards.
I like how it broke. And two, I saw how it looked over.
You thought I had a more efficient workout going. I did too. 5 more minutes. Okay. Anyone still working, or we can start going over it? Okay. So let's look at this. So we're looking at free body diagrams for the first problem. So first we want to look at it at the top of the circle, at the top of the bucket. Okay. So what forces are acting on my bucket? And I want to remind you of the process. Step one is gravity affecting the bucket. Is it, Noah? Yeah, it is. So we've got FG going down. Now, the second step, is there anything touching the bucket? Is there? Looks like it. What is it? The rope. And so to label a force from a rope, we would call it tension, right? Okay, so the free body diagram basically looks like this. So bonus question, what would the centripetal force be equal to for this problem? Tension plus gravity, because they're both going toward the center of the circle. Now, talk about the water. So I'm going to not draw a square, I'm going to draw a circle because that's clearly more water-like. Okay, so the water in the bucket has different forces acting on it. So let's do the same procedure. Is the water affected by gravity? It should be. And I'm actually really sad because I forgot to include gravity on the solutions. So for those of you looking at the solutions and not seeing gravity, yeah, my bad. It happens. But the next question is there something touching the bucket? The water, my bad. Yeah. There is something touching the water. What is the thing touching the water, Noah? The bucket. Okay, which way does the force from the bucket affect the water?
Everywhere.
Okay. So the side to sides are gonna cancel out on each other. There's gonna be a net force from this bucket. In what direction? Yeah. Yeah, down. So there's going to be a force from the bucket going straight down. All right. And what would we label this force as? It is a normal force, Fn. Why is it a normal force, Zach? Okay, surface being the bottom of the bucket. Yeah, so that's not incorrect. That's fair because all normal forces behave that way, right? But normal force is when one object cannot pass through another, right? So where would that water go if the bucket had a hole in it? It would probably fly out this way, right? So that doesn't happen because the bucket keeps it locked in the circle with a centripetal normal force. Okay, so we have the normal force going that way. That is an impressive straight line that just magically popped up. Okay, so then we go on to the bucket when it's at the bottom of the ramp. How does this work? Bucket at the bottom. Noah, give me one of the forces.
For the bucket and bomb.
Gravity. Very proud of that one. And then Zach, give me the other one. Tension. Which way does tension go? Up. And so if I wanted to find the centripetal force on the bucket at this location, what would I have to do? Tension minus gravity, because gravity is going away from the circle and tension is going toward the center of the circle. So that's how centripetal force works. Adding up everything going toward the center, subtracting everything that is not. Okay. Now we're going on to number 2. The bucket completes a full rotation in 3 seconds. So what is that value that they gave us? It's the period. So we'll set that equal to big T. Okay, if the bucket has a mass of 6 kilograms, including the water, derive an equation for the tension in the rope at the bottom of the circle, only using RG. G, and pi. Very interesting. So first, let's start with an equation for centripetal force, because that's what they want. Actually, no, for tension. So if they're solving for tension, then this is what we have to do. We have to, basically, we want to figure out the sum of all the forces. So normally when they ask for a force or an equation for a force, you're going to find the net force. In this problem, that's going to be the centripetal force. So if we're talking about at the bottom of the circle, it's like we said before, the centripetal force should be equal to tension going toward the center minus the force of gravity from the bucket. Okay. Now, what do I set this equation equal to? FC is equal to, it is mv squared over r. It's skipping over the MAC part of the equation, right? But we can get there. So the M, I'm not too worried about because they gave me M, so I could replace it with 6, right? And then R, they gave me is R, big R, so we'll leave it as big R. V squared. So this equation looks like it would get us pretty close, but we still have the problem of V and this FG. So if I solve for tension, I get tension is equal to 6V squared over big R plus FG. Okay, so how could I get rid of FG? Let's pick one. What could I replace FG with? MG. So I can keep everything the same, but I could replace FG with MG. And I know M is 6. So I will have 6V squared over R plus 6G. So I'm almost there. The only thing is I have that velocity and I don't know how to get rid of the velocity. Is there an equation I could use in order to get rid of the velocity or replace it with something better?
Yes.
What is it?
2 pi r over t.
Yeah, so velocity is 2 pi r over t, for t being the period. But I thought I wasn't allowed to use big T. We have t. It's 3, right? 3 seconds for the period. So 2/3 pi times r is basically what the velocity is going to be equal to. And so we can plug that back in down here and we could get our final result. So period being equal to 6 times 2/3 pi r, all of that squared, divided by r plus 6g. That is the final answer, unsimplified. I think I give a slightly more simplified version in the solution.
But we don't have to.
You don't have to simplify. One of the best tips I could give you to save time is that once the equation's set up and you think it's right, move on with your lives. Because if it's technically correct, they have to give you the points. And the only thing you can do by spending 10 minutes simplifying is you waste time and you might mess up. So as long as it's correct, you're good. All right. Lastly, if the radius is 1.2 meters, then what is the average speed of the bucket? So basically, you apply the same equation I just asked of you, 2/3 pi times the 1.2 meter thing. And then you end up with like 2.4 or something like that. Let me just double check. 2 times pi times 1.2 divided by 3, 2.51 meters per second. Okay. So any issues there? Any questions from anyone on Zoom? You guys doing okay? Okay. Let's go on to the next question. A satellite is orbiting Earth from a height of 3 times Earth's radius above its surface. Let Earth's mass be big M and let satellite have a mass of little m. Number 1, find an equation equal to the acceleration due to gravity at this altitude. Number 2, use the equation from the question above to find a second equation equal to the speed of the satellite. 3, draw a vector for the velocity of the satellite and a second vector for its acceleration. Lastly, it says lastly, but it's question 4. If the satellite's mass doubled and its radius increased by another 4r, then what would happen to the force of gravity between the Earth and the satellite? And 5, would the magnitude of the gravitational force felt by the Earth change during equation 4? If so, which object would experience the larger force of gravity? Explain. That's a full 13-minute question for you. Do your best. We'll take the last couple minutes to go over it. Was that Noah or was that me? Okay. You having a good time there, Noah?
Can you move it up so I can see the question? Oh, that works too.
Hold it, what? See.
Your chair
that's
just.
a long string.
Oh yeah, there's a
I told
spring.
you, I asked you why they were-
There's a spring on the floor. Yep.
Why is there a spring on the floor?
Isn't it obvious?
No, not really.
Oh, okay.
Are you trying to show the class mod 9?
No,
Spring
Noah,
waves?
is this what we should be talking about? How many AP problems are going to be about spring waves?
None.
Oh,
Yeah.
I keep forgetting to put that one. That's been a thing I've done since 2018. I've made like 5 or 6 circular motion tests since then, and I never tell them which way it's going. I promise the AP exam will be better than me. Just pick a direction. Well, it was gonna be last, and then I wanted to ask one more question. Isn't that great?
Shoot, Mr. Haberly,
Yes, Tom.
I have to head out.
Yes, I figured you would. All
I completely missed that.
right, good luck. Sorry.
Thank you.
Bye. For 1 more minute, then we'll talk about it. All right. So let's chat about it. So find an equation for the acceleration due to gravity at this altitude. So the base equation, G, big G, M over R squared. So I gave you, you're allowed to use any constants, so G is fine. You're allowed to use big M because I gave you big M for Earth's mass. The question is, how much is the radius? And so I said it's 3 times Earth's radius above its surface. So that means that you have 1 radius here, and then you have 3 radiuses there. So the total radius is going to be 4r. So you have Gm over 4r squared, which is exactly what I was looking for. If you really wanted to simplify, it would be Gm over 16r squared. Okay, so it would essentially be 1/16 the acceleration due to gravity that you would get on the surface. So we got that one. Use the equation from the situation above. So G is equal to big G M over 16r squared. All right. And find a equation for the speed of the satellite. Okay. What did I do for this? Oh yeah. So G is going to be equal to the acceleration due to gravity, which should be equal to the centripetal acceleration of the orbiting satellite. Because remember, for any object in perfect circular orbit, the force of gravity is the centripetal force, and the acceleration is the centripetal acceleration. So we had big G m over 16 r squared equal to v squared over the radius. The radius being, what is it? Radius being 4r, right? 4 times Earth's radius. So solving that for v, we have these radii cancel, at least one of them. And then you multiply it by 4 and find the square root. So you get g m over 4r in the square root is equal to v. I think I might have forgotten this 4 on the solutions. I'm just great today. A+. But yeah, this is what the equation should look like. How do we do so far? That's okay, I did too. That means we would both not get a 5 on the test, but still, you're fine. You don't need 100 to get a 5. I need to make that completely clear. Normally people get us like a 70-ish. So draw a vector for the velocity of the satellite and the second vector for the acceleration. So you just had to pick a direction because I didn't give you one. V and centripetal acceleration. This was kind of my hint for you for number 2. So if you didn't know number 2 and you went to number 3, reminded you that the acceleration is both the acceleration due to gravity and AC. But as long as you had this set up with a 90-degree angle, didn't really care what direction the velocity went. The AP exam will obviously be better. And lastly, if the satellite's mass doubled and its radius increased by another 4r, then what would happen to the force of gravity between the Earth and the satellite? So you set up the big gravity equation, G m over r squared. Now you're going to adjust everything. So G stays the same. The big M of the Earth stays the same. The satellite's mass doubled. And the radius it started as 4r, and then it became 8r. So it essentially doubled. Okay. So that means that you could do this a number of ways. You could plug in 8r and compare it to the first answer. So 8r, all of that squared. And so you get G m, well, forgot the 2. Pulling out the 2 G m, not enough space. 2, oh my God, I'm tired. 2 G m over 64 r squared. And so this is basically the same thing, just over 32 with the 2's canceling. So our first answer, if you plugged it in and you actually figured out what the force of gravity was getting, it would be G m over 16 r squared. Okay, so what happened to it? It's half as big because you've got double the number on the bottom there. And so one way or another, you figure out that the force decreased by a factor of 2. You could say multiplied by a half or any of those other things, as long as you are clear. Okay. So no questions, all good? And then last was a special one. Would the magnitude of the gravitational force felt by the Earth change during question 4? So I changed the mass of the object of the satellite and I changed the radius the satellite's at. Did the force of gravity affecting Earth change?
You look at Zach too.
I did. I did look at Zach too. The answer is yes. It did change because when you calculate force of gravity using this equation, which one are you calculating force for? The big M or the little m? It's both. They're interchangeable. It doesn't matter. Okay. The force from Earth to the satellite is going to be the same as the force from the satellite to Earth. They're both going to weigh the same compared to each other. Okay. So that's one of the things I said in the beginning of the year. So if I weigh 185 pounds on Earth, Earth weighs 185 pounds on me. It's Newton's third law. Every action, there's an equal and opposite reaction. For every gravitational force, there's an equal and opposite gravitational force. So this answer here, would the magnitude of the gravitational force felt by the Earth change? Yes. And if so, explain. Well, if you change one of the masses, you're going to change the force for that one, and the other force has to change with it because the forces must always be equal. They are what's called a Newton's third law pair. All right, and we went 5 minutes over, which is better than I thought we would do. The last chance, any questions for me from Brianna, Zach, Max, Noah? All right, guys, keep working on those web assigns. And I'm actually warning, I am not going to be in class tomorrow. There will be a sub. I want you guys to work on the short answer questions I had passed out. All right. See you guys.